Small polymorphic types are giving you superpowers in C#. There are plenty of videos on this channel where I have already demonstrated how that works. We are finally getting union types, more superpowers for us, I'm telling you. But now, suppose that you already use such small immutable polymorphic types such as small hierarchies of immutable records, for example. There is a constant question which I hear all around. How do you persist that in a relational database? So let's do precisely that. That is the only thing I will do in this video. There are just a few steps you need to make, and when you make them right, it will just work. So let's begin and you will see. There is a very simple class here. It has a couple of scalars, the foreign keys and all, but it also has this small polymorphic property. This entire class is a stripped down model of a money transfer. I have removed all other properties and only left this one that matters. The 4eyes approval record keeps track of employees who have approved the money transfer. It is abstract and it can take several shapes. That will cause troubles when storing it into the relational database. You can already start worrying about that if you wish. These are the possible shapes of the 4eyes approval. It can be not required, or required but pending with nobody approving yet, or approved by only one person where we need one more, or fully approved by two distinct persons. Eventually it can also be rejected. So far you have seen this hierarchy of records as algebraic types. They are handy to represent various shapes of data, but they complicate persistence. That raises a question: is it a good trade-off? Trading a richer representation for a more complicated persistence? Well, it becomes a good trade-off when we observe behavior. Pending approval supports an operation to add an approver. And so does the partly approved variant. No other type supports this operation. This hierarchy of records gives us type safety. That is why it is so useful for us. Reject is another operation. It exists on all subtypes except the one that requires no approval. Watch my previous video to learn how type system works for you. My worry in this video is persistence. So the question is, how do we persist this in a relational database? And here is the first critical observation. All types in this model are deeply immutable. That immediately puts Dapper as the natural choice. Using EF core means to either fight against its principles or to first refactor this solution into a mutable variant. I am not going to do any of those. I might do it in a different video. So in this video, the Dapper it is. This SQL script will create the tables, and I will add the transfers table. There come the scalars, foreign keys, and that is where this video truly begins, because now we need to represent this hierarchy of small types in form that we can store in a relational database. There are two principal ways to store polymorphic types: table per hierarchy and table per concrete type. There is the third approach, table per type, but it is rarely useful. You can read about these on the internet. I will only show you the table per hierarchy because it is the best fit for small polymorphic types. So there would supposedly be a table. This record will model it, and it can represent any subtype of the base record type. In order to know which particular type the row is representing, it must have an explicit discriminator field, typically a string, which is varchar in the database. And then you put all the properties from all the subtypes as a union. But be careful, a property may only exist on one or a few subtypes, but not on the others. Any such property must be nullable in the database because some rows won't have it. That puts stress on validation because not all combinations of nulls are valid. For example, partly and fully approved variants require a non-null first approver. All other variants forbid non-null values because such property does not exist on those types. This record type is a useful utility which you may define in the database layer, not here where the model is. Dapper works pretty well with such records. However, I will comment it out because I plan to use dynamic and anonymous types with Dapper in this demo. You can choose between those two options in your designs, they both work. What is more important, however, is the question of the additional table. Will I add another foreign key here for the approval status of the transfer? No, I won't. And understanding why is the core reason for you to watch this video. So here's the observation. Small, immutable hierarchies of records do not have an ID. The union types, when they come to C#, they won't have an ID. And we don't create a new table for something that doesn't even have an identity. So what are they? Are they values? No, they are not values either, because values are not polymorphic. A value is just one type and it doesn't have variants of it. There is no ID, therefore discriminated unions and union types go in the same table, database table, where the principal entity belongs, the entity that holds them. You will see me do that, and I will, as I said, I will show you the steps you need to reproduce in every case of this kind, and it will simply work. Before that, let me steal a moment of your time to remind you of something. This channel is free and everything on it is free, but only thanks to the patrons, the people who are supporting my channel on Patreon. So if you like what you are learning on this channel, if you want this channel to remain free forever for everybody, then please consider joining the growing community of patrons on my Patreon page and become a sponsor. Patrons have access to the source code of this video and all other videos on my channel, and they have access to some discounts which I occasionally offer on Patreon. Thank you very much. Now let's get back to code because we need to implement that hierarchy of records right inside this database table. So I will first define the approval kind, which is the discriminator column. Then I will add all the scalars as nullable columns. That's very important. But then we must also protect the database from invalid inserts. We do that by defining the check rule. Carefully list all the valid combinations of nulls and non-nulls depending on the discriminator. I can easily create a database and all the tables. And so we can finally start using this system of immutable types and its database representation. The demo code first establishes a database connection and then loads the two GUIDs which the transfer requires as foreign keys. Everything is ready to instantiate the transfer in pending state. It contains the pending approval instance with nobody approving it yet. The next step is then to implement support for the database insert statement. This is the utility class in the data namespace. I won't implement any repositories and the like. That's not the goal of this demo. I will show you the bare Dapper code, which you can then use in whatever abstractions there are in your project. There will be the utility that creates a new transfer in the database. The SQL code is straightforward, just an insert statement. Both the scalars and the polymorphic record fit in the same database row. We explained that. But then how do we translate a record instance into those flat table per hierarchy columns? We need a special mapping method for that. This utility method takes a record and returns its encoding in the transfers database table. Then simply apply it to the record and collect the fields. Put them into the parameters and Dapper will insert them along with the rest of the transfer data into the same row. That completes the insert operation. It is very simple once you understand how record mappings work. Let's repeat the same process for the update statement. Again, the SQL code is straightforward, but in order to obtain the fields, we must map the record again. Pass the fields to the command and they will find their way to update the database row. It is remarkably simple once the mapping is there. But there is one immensely important detail to notice here. This implementation, which I have shown you, supports changing the runtime type of the record. EF Core has no support for that. Once the subtype is established for an entity, it stays. You must implement manual update to change it. With Dapper, you simply update the discriminator. Alright, let's move on. Deleting the transfer is trivial, I will skip it. What I do need, however, is a way to get a transfer given its ID. Reading the database row and quitting if ID was not found is straightforward again, it's just SQL code. But the complication comes with these encoded fields again. We need another utility method that will decode them back into a polymorphic record instance. If we had that, we would obtain the approval object. And that is all we need to instantiate a valid transfer object to return. It was easy after all. The key is in being organized. We need to define clean mapping between record instances and flat database fields. Beyond that point, everything is easy. This will cause an insertion of a transfer row into the database. I will prepare a utility function to read the transfer and print it out. So reading it, printing it out. I can report the transfer to the console, but that will be the transfer as it is in the database, not in memory. So we can prepare for the updates. These two persons will approve the transfer. For each of them, I want to check if it is possible to add an approver. That is the type system working for me. It is impossible to invoke a method that would cause failure. Watch the previous video if you have any doubts about this technique. If the transfer cannot accept a new approver, just quit. Otherwise it becomes interesting. Apply the non-destructive mutation to obtain the new modified transfer instance. Then pass it to the update operation. That will not only change the transfer row, but also change the runtime type of the approval inside it. We will see that in the report, which again displays the state in the database, not in memory. So let's run the application. Here you can see how the approval status evolved from pending to approved by a single employee to approved by 2 employees. That proves that the encoding of records worked just as expected, all using Dapper. This is the central element in the demo. You would encode record instances and decode database rows back. That is because the database representation is always flat, and you have to flatten your models to fit the relational database model. However, this mapping and decoding back into the object model will let you keep using the rich, deep domain model again with no constraints.